Good afternoon, everyone. On behalf of the Atoms Group, I'd like to welcome all of you to our 2022 seminar series. And we are very honored to begin this year by receiving Professor Keith Gubbins. Professor Gubbins received his BSc in chemistry at Queen Mary College in London with first-class honors in 1958 and received his PhD at the King's College in 1962. While his PhD research focused in kinetics of reactions in fluidized beds, he moved to the University of Florida, where he quickly advanced to full professor in 1972. In this position, his interest over statistical mechanics started focusing mainly into fusion and solubility of gases in electrolyte solutions. There, he co-authored the first book aimed at practical application of statistical mechanics, playing a big part in introducing this topic to the chemical engineering field. Over the years, Professor Gubbins has also contributed to the introduction of molecular simulation into chemical engineering, focusing his research on the development of reliable predictive methods based on statistical mechanics for phase equilibria, equation of state for complex fluids, nano-porous media, and transport properties. In 1998, he moved to North Carolina State University as the W.H. Clark Distinguished University Professor. One of his most significant contributions is the development of the SAF theory through perturbation methods, an approach that has been successful even for strongly associated liquids. He was also one of the first to realize the potential of statistical mechanics for modeling adsorption phenomena, resulting in the density functional theory method, which is widely used in analyzing adsorption isotherms and calculating pore size distributions. Professor Gubbins is the author and co-author of approximately 500 research publications, and along with his 4 books, they have received over 36,000 citations worldwide. He has been the supervisor of over 90 PhD students and postdoctoral researchers, many of whom now hold faculty positions all over the world. Once again, thank you so much, Professor Gubbins, for being here with us, and feel free to start your presentation whenever you're ready. We're gonna share your slide, and then you can start. Okay, I think we're all set.
Okay, good morning, and apologies for this mix-up with the slides. So I'm going to talk about a phenomenon in porous media, which is the compression of the confined nanophase, and this occurs because of the intermolecular forces from the walls of the pores. So it doesn't always occur in all systems. The nanophase has to wet the walls in order to see this enhancement. So if we can go to the next slide, these are some of the people that have been involved in this work. This is my colleague, Eric Santizo, who I think you know because he's given at least one talk in this series. And the next 3 people here were PhD students in our group, but have finished now. And the 2 people at the bottom are professors that we collaborate with who are experimentalists. And so Margaret Slavinska-Barkowiak is a physicist. She specializes in experiments on dielectric phenomena and also neutron scattering and other methods, particularly applied to confined fluids. And Katsumi Kaneko in Shenshu University in Japan is an expert on confinement effects, experimental studies primarily. So the next slide, I think, this is a quote from Lord Rayleigh. In 1892, this reference here, he commented that the surfaces of bodies are the fields of very powerful forces, of whose action we know but little. Well, that was 1892. Now we know a little bit more. And the main thing we know is due to a man named Fritz London, this reference here. This paper is in German, but he explained the so-called van der Waals forces or dispersion forces. They give rise to the dispersion of light. And so all molecules and ions and particles have these London forces, and they're due to oscillations of the electron cloud. So it wasn't until quantum mechanics was introduced that people could understand this type of force. And so a molecule like argon that doesn't have electrostatic forces or carbon, these atoms would still have weak attractive forces. And this would cause argon, for example, to liquefy. If you cool it down to a low enough temperature, we know now that it would liquefy. So the next slide is a brief outline. I'll give some introduction, and I'll then show some molecular simulation results where we can actually calculate, given the forces between the molecules, we can calculate pressures in these systems. Excuse me. And these pressures are, in the case of these confined phases, they are very inhomogeneous. The density and composition varies rapidly as you move around inside the pore. And so the pressure is a second order tensor, which makes life more difficult, of course. And so in some of these cases, particularly for absorption in carbons, which has a very strong force field from the carbon, you see pressure enhancements. And we can see this in our simulations. I'll show some results. And I'll give some examples of applications where experiments have been done that show or seem to indicate very high pressures in some cases. And finally, I'll close with some comments about possible future applications of this phenomenon. So if we can go to the next slide. So we're going to be talking about nano-porous materials. And in the last few decades, people that do synthesis have discovered many new synthetic materials, things like metal organic frameworks and organo materials that can have controlled pore sizes and to some extent controlled pore shapes. And these are some of the current applications. So there are traditional applications like chemical separations. We can separate xylenes by absorbing mixtures into zeolites. And if we choose the correct pore size, we can separate meta and ortho and para-xylenes, for example. So there are many examples of this case, this kind of application. And we can use this for environmental remediation. We purify our water supply using activated carbons that remove organic contaminants preferentially absorbed in the carbon. But there are also many more recent applications, such as drug delivery. So we encapsulate the drug in a porous medium. And this medium is designed to release the drug at a given rate determined by the diffusion. So that the drug is allowed to enter into, say, the bloodstream in some controlled way. There's a lot of interest in energy storage. We can store natural gas in these materials at some fairly high density. And nano manufacturing is, of course, a potential application that is being heavily explored. There are other applications that are probably not so central to chemical engineering, such as sensors and semiconductors. So the next slide, I think, so shows some experimental evidence. So we do not yet have an accepted way to measure the pressure in the pore, because the pressure is a tensor. And so it has a normal component, normal to the pore wall. We can measure that in principle because it presses on the wall, it makes the wall move, and it can also change the spacing between the atoms in the solid. And so you can see evidence of this from X-ray or neutron diffraction. And if you know the modulus of the material of the solid material, you can convert that to a normal pressure. I'll show an example of that in a moment. But the more interesting pressure usually is the pressure component that is parallel to the wall. We call that the tangential pressure. So that pressure doesn't press on any solid surface. It doesn't press on the wall. The wall's basically unaware of the tangential pressure. And so it's difficult to think of an experiment to directly measure that. We think it can be measured by combining experiment with molecular simulation studies, and I'll mention that later in the talk, but that hasn't really been done yet to any significant extent. So this first application on the left, I'll talk about in more detail. These are carbon nanotubes which have sulfur absorbed inside them. And so you have a vapor, which is sulfur, at some low pressure, less than 1 bar. And the sulfur is absorbed into these tubes. And as you vary the diameter of the tube, you can see phase changes. So you may see a phase change from an insulator to a conductor, for example. This work was done by the group of Katsumi Kaneko in Shinshu, and he's also studied high pressure effects where crystals form in the pore. So this is a schematic of a potassium iodide crystal in the pore. This is a high pressure effect. There's no chemical reaction involved. And this is our experiments done by a group in the University of Manchester, where they looked at various nanophases confined in between a slit pore made up of 2 graphene sheets. So if you remember, a man named Andre Geim got the Nobel Prize. He was in Manchester in this same department, and he was able to prepare a single graphene sheet and then studied the electronic properties and various other properties. So these are some indirect experimental evidence. We're not actually measuring directly the pressure, but we're seeing evidence that strongly suggests high pressures. And so in this particular application, it's in this paper by Vasu et al. They observe aqueous solutions in these pores. And inside the pore, the aqueous solution becomes very reactive. And we believe that you could carry out many reactions in aqueous solutions by confining them in the appropriate pore of the appropriate size. This is a pore, again, of graphene with graphene walls, just single layers of graphene. So if you look at bulk water, there are some beautiful experiments done by Ulrich Frank, a physical chemist in Germany, where he studied high pressure effects. And this was his specialty, really. And he showed that at high pressures, water becomes much more ionized. And we think this is the origin of this strong reactivity of the water. So next slide, please. Here, this is an experiment, again, done by this group of Vasu et al. In Manchester. So they did a range of experiments where they observed what seemed to be high pressure effects. So their paper is called Van der Waals pressure and its effect on trapped molecules. And so here is a molecule of triphenylamine, and this is what it looks like. So there are 3 phenyl groups. There's one here, one pointing upwards, and one here. And in the middle, there's an amine. And so this is what it looks like if it's at low pressure, say atmospheric or less. And then they do Raman spectrum. So they get the Raman spectrum at for the bulk TPA, this molecule, at low pressure, about one bar. And they see these Raman shifts, and they see a big peak here and another one over here, which, if you're familiar with Raman, tells you a lot about the structure of the molecule. And then they do the same experiment, Raman spectrum, but now they have this molecule confined in a slit pore composed of graphene sheets. So these are single graphene layers. And now the molecule appears to be very compressed. Instead of having this configuration, it has, this is schematic, but this is what the experiments indicate for the structure. And so this tetrahedral structure's converted to something that's relatively planar, and they get this spectrum here. So there's a shift in these peaks. And they believe this is because there's very high pressure inside this pore. So then they go back to the bulk TPA and they redo the experiment at different pressures, and they keep increasing the pressure. And then this spectrum that was at low pressure becomes more and more similar to this spectrum, which is for the confined phase. And so now you've got a bulk phase. You don't have any pore, but the molecules around a given TPA molecule are pressing on it so hard because of the high pressure that it's deformed. So they chose this molecule because they knew that it would deform under pressure. And so now they can estimate a pressure, some sort of thermodynamic pressure inside this pore, and they find out that it's about 12,000 bars. So they then do other experiments. They did boric acid. They see the same sort of effect. They match the bulk spectrum to the confined spectrum, and they find a pressure of about 9,000 or 10,000 bars. Okay, next slide, please. Okay, so how do we explain this? Well, what's happening is that we have a molecule in the confined phase. So this is, let's say this is argon, the simplest possible molecule, this green molecule. And it's interacting with a graphene sheet here. That's these blue atoms. So this is not to scale actually, but these atoms are forming a graphene sheet. And this argon molecule interacts strongly with this surface. So this pink circle represents a sphere around the argon. It's the range of interaction schematically of the argon with the graphene sheet. And so if you look at this from above, now we're looking down on the argon molecule on the graphene sheets below. You can see that this argon doesn't just interact with one carbon atom, it interacts with a lot of carbon atoms, maybe 20 or 50 carbon atoms. And in the case of carbons, the nearest neighbor distance between two neighboring carbons is very short. It's 1.42 angstrom units. So this is the very strong covalent bonds in the graphene sheet. And so there's a very high density of carbon atoms on the surface. And it's this high density of the carbon that gives you this very strong force field. And I'll show you this force field in just a moment. So here we had a flat sheet. So this would be like the experiment of Vasu et al., where they had molecules trapped between two graphene layers. But if I curve this surface, this is now a double-walled carbon nanotube, you can see that there would be more molecules inside this pink circle. So you would get an even stronger force field if you had a carbon nanotube than you would if you had a flat sheet. So you can control this force field to some extent by this curvature, and we can make carbon nanotubes with very narrow diameters down to just a few angstrom units or nowadays, and we can vary this diameter, and we can vary the chirality of the tube. So we have some control. So if I go to the next slide, if we look at the forces, we have good intermolecular potentials for argon with carbon atoms, probably within a few percent of reality. If I consider the interaction of the argon with a single carbon atom, I get this blue line. So this is the force in piconewtons, and this is the distance from the surface of the argon atom. So as I move the argon atom away from the surface, so I move it in this direction, the force gets weaker and eventually goes to zero in fairly short distance, because these are just London forces. So there is a minimum in this force here, and the force goes to zero about here at about 3.6 or 3.7 angstrom units. And there's a shallow minimum. So you might think, well, the force field is pretty weak. But if you add up all the pair interactions with all of these carbons, you get this black curve. And so now this well is about 20 or 30 times deeper than it was for the single carbon atom. And this is the reason you get this strong compression effect. So if you remember back to your high school, you saw experiments in physics where you took a powerful magnet, held it near iron filings, and the filings just go as fast as they can onto the magnet, and they're all clustered together. And they're pressing against each other because they're all so desperate to get onto the surface of the magnet. So it's that kind of thing. It's not an electromagnetic interaction, of course, it's electrostatic, but that sort of physical picture is how we imagine these argon molecules jostling with each other, trying to get onto this surface. So you can look at other surfaces this way. If you look at silica, so there are a lot of porous silica materials and a lot of porous metal oxide materials, then that interaction is weaker. But that weaker interaction is mainly due to the fact that the density of silica atoms, it's much smaller on the surface than the density of the carbon atoms on the graphite. But you still get a big effect. You get this red curve, and you can see that this minimum is about minus 60 units here. Okay, so this is what we feel is the origin, the physical reason for these compression effects. Next slide, please. Okay, I hope this will work. I'm going to show a video. This is now molecular dynamic simulation, where you have a graphite surface down here. That surface is not shown, but it's the lower limit of this box. And now we're, let me just stop this for a moment. We're showing the interaction with the wall is 1.5 kilojoules per mole. And so this is a fairly weak interaction. And here, near the surface, we have a liquid-like phase, a multi-layer absorption. And up here, we have a gas-like phase. And if you watch this video, you'll see that the molecules at this wall strength, the molecules are acting in a fluid-like way, even near the contact with the surface. But we're going to keep increasing this energy, this force from the wall. So we're increasing the force field. And what happens at a certain point, right about here, is that this contact layer becomes crystalline. And then as we increase it more and more, as we increase this more and more, the other layers gradually become crystalline. So if you watch this density, in the beginning, it was 6 atoms per square nanometer. That's the density right next to the wall. But as we increase this force field, the density goes up, and now it's 9.39. So it's gone up by about 50% as we started with a weak force field and increased to the strong force field. And we see this in our simulations with other molecules. This is Leonard-Jones argon, but we see it all the time with different molecules. The next slide shows a view looking down. So we're looking down on the surface, and the graphite is below these white molecules. So these white molecules are the argon atoms on the surface, and it looks like a fluid. And if I start the simulation, is it working? Yes. So it's the same simulation, but we're just showing the contact layers. So here, the wall strength is 1 kilojoule per mole. And now we've increased it to 1.56, and the density on the wall has gone from 6 molecules per nanometer squared to 6.9. Now it's gone up even more. You can see it becoming denser. It's still a fluid, but now it looks like a solid. It looks like a hexatic crystal. And these molecules are on lattice sites, but they're vibrating about the lattice site. There's very little diffusion because it's a solid. And as we go up in wall strength, it becomes more and more confined, and these molecules become denser, and there's less motion. Okay, so I want to show now some results from molecular simulations. If we go to the next slide. Yes. So first, let me say a little bit about the pressure. So the pressure is a second order tensor because there are 2 directions involved in this situation. There's the direction of the force, and there's the direction of the surface that the force acts on. And so if there's no stress on this system, the off-diagonal elements of this tensor go to 0, which is good. Now we have 3 diagonal elements. So this is the pressure in the x direction acting on a surface oriented in the x direction. And in other words, a surface that's normal to x. And similarly, this is the pressure in the force in the y direction acting on a surface in the y direction, and so on. So if you write down the statistical mechanical equation for the pressure, I'll show it to you in a moment. There's a kinetic part. So this is the ideal perfect gas part. So there's no interactions in this perfect gas. And so this pressure is just coming from the kinetic energy of the molecules. They're bouncing off the walls, and this creates a pressure. And then there's a configurational part due to the intermolecular forces, which is added to that. And so it's the sum of these 2 terms. If we go to the next slide, here we have a simulation cell. And so this cell is made up of 2 parallel walls. Each wall has 3 graphene layers. So these are carbon atoms. And there's a pore width, which we call H. And outside here, we have a bulk gas. And inside, we have the confined nano-phase. So this is how experiments are done on porous materials to get characterization. So people measure the absorption isotherm, they change the pressure of this bulk gas, and they measure how much is absorbed in these pores. So from the symmetry of this, there are 2 pressures. There's one in the normal direction that's acting on this blue surface. So that would be the PZZ. So I've called this direction the Z direction. So PZZ is the normal pressure, PN. And from hydrostatic equilibrium conditions, you can show that PN is a constant. It's the same value as you go across this pore. And so the pressure on the wall is PN, but the pressure in the middle here is also PN in this direction. And then the other pressure, the tangential pressure, PT, because of the symmetry, PYY and PXX are equal, and they're equal to this tangential pressure, and that acts on this green surface. So next slide. Yes, there is a technical problem when you go to the nanoscale in that while this kinetic part is well defined, even at a point, it's just given by the ideal gas equation. P is equal to rho KT. Rho is the density. but the configurational part is not well defined. And so it depends on how you do the integration over the intermolecular forces. And this was recognized in an early paper by Irving and Kirkwood. And they said, well, we're going to, the problem is that the forces act between pairs of molecules. And so that force is well defined, but it's arbitrary where you assign this force in space. So you could assign it to this point or this point. These are different planes, XY planes, or you could define it to any point in between here. And so the pressure is not well defined. You have to say, I make an operational definition of the pressure. And let's say we adopt Irving and Kirkwood's definition. But if we have time, I'll show some other definitions and how they vary. But you can integrate over a small region of space here. And you can show that all of these different definitions give the same coarse grain pressure. So I don't want to go into that because it's a lengthy discussion and it's an ongoing research area really to discuss it. So the next slide shows the equations. So these are just standard statistical mechanical equations. This is the kinetic part. So you have to remember that the density now depends on the distance from the wall. And this is the configurational part. So this is the force in the z direction for an alpha beta pair of molecules. This is the two-body distribution function. And this d lambda, you're integrating over the path from molecule 1 to molecule 2, basically. So if you adopted Irving Kirkwood, which we have here, that's a straight line path. Now, in our field, we talk a lot about the pressure tensor, but in other fields like fluid mechanics, those people and mechanical engineers would talk about the stress tensor. And these are the same thing, basically. They differ only by a sign. So if you're used to the stress tensor, you can think of all of this that I'm going to talk about as showing the stress tensor in the system. So the next slide shows, I think, some experimental results and some simulation results. So this is a situation where we're looking at the normal pressure, normal to the wall. These are experimental results. They're obtained by X-ray diffraction. So this is the group of Slavinska, Bartkowiak. So they did X-ray and neutron diffraction. And they observed the small changes in the pore width and small changes into the spacing between the graphene layers in these carbon fibers. And from that, because they knew the modulus of the carbon roughly, not very accurately, but they knew roughly what it was. People had tried to measure it. And they got these 2 points. So this is a pore of about 0.86 nanometers in width, but there's a distribution of pore widths that not all the pores are exactly the same width in these carbons. And so there's an error bar here. This is the range of most of the pore widths. And there's an error bar on the modulus. So these are not, you're not able to get very high precision, but it agrees with the simulations pretty well. This is the simulation results. And these peaks occur because of layering in the pore. So this would be a pore that just accommodates 2 layers of water molecules. And then as you make the pore larger, there's not enough room for a 3rd layer. But when you get to this critical pore width, a 3rd layer starts to form. And so you get these oscillations. So in this case, for the water, the pressures normal to the wall are a few thousand bars. Now, the bulk pressure is 1 bar. We're actually at the boiling point of, we're at 300 Kelvin. So we're at a compression of 1 bar. So we're getting an enhancement in the pressure, in the normal pressure of about 3 or 3.5 orders of magnitude here. from both the experiment and the simulation. The next slide shows a more complete picture. So this this is a bigger pore. It's a slit pore. These are simulation results. And so you have 3 graphene layers in each carbon wall. And this is a width of 15 molecular diameters. This is the diameter of the argon atom. So you, you have many layers of argons absorbed in here. Out here you have a gas, which is at the boiling point of argon 87.3 Kelvin. And so the pressure is 1 bar out here. And these are the pressures found. This is a Monte Carlo, grand canonical Monte Carlo simulation. So this is the tangential pressure. So this does depend on the distance from the wall. You can see it depends strongly. So you get this very big peak. This is the layer of molecules next to the wall, and you're getting a pressure of about, this is an Irving-Kirkwood pressure of about 19,000 bars. So now we've got more than 4 orders of magnitude increase in the pressure over the bulk phase. And then as you go away from the wall, you get these oscillations. So the second layer is only about 6,000 bars, but still nearly 4 orders of magnitude. And even in the center, this is the center of the pore, which is enlarged in this snapshot, you're still getting oscillations that are up to 300 or 400 bars. Now, the normal pressure here, because we've chosen this particular pore width, this particular pore width of 15 sigma, this pressure is quite low. It's only 27 bars and it's constant. It's given by this black line, which looks close to 0 because this is a compressed scale. So we get these very large tangential pressures, and we think that it's mainly the tangential pressure that Vasu et al. Was seeing in their experiment on triphenylamine in the graphene slit pore, because the tangential pressure is generally much larger than the normal pressure. So this is due to the fact that the molecules next to the wall are very compressed in the the XY direction, the direction parallel to the wall. Okay, next slide. This is just showing the effect of wetting. So in the last slide, I showed argon as the fluid in the pore, but different fluids will wet the wall differently. For example, mercury is very, very non-wetting, and it would try to form a spherical drop on the wall and not, have a contact angle of 180 degrees, whereas argon has a contact angle that as if I remember correctly, is about 100 degrees. Sorry, about 60 degrees. So argon wets the wall quite well. And there's a molecular parameter we call the wetting parameter that's very useful as a measure of wetting. So wetting, how well the phase wets the wall, is a crucial variable in all of these results. And so the stronger the wetting is, this is the tangential pressure, and this is the wetting parameter. The stronger this wetting is, the greater is the tangential pressure, and also greater is the normal pressure. And so in carbon, molecules like inert gases, argon, krypton, xenon, and molecules like organic molecules, heptanes, the hydrocarbon molecules, neopentane, very strong wetting, high wetting parameters. And they on this diagram, the strongly wetting fluids would be around this area where alpha is around 3 or 4. So tangential pressures in kind of the 20,000 bar range, which we saw before. Next slide, please. So I want to show you in the remaining time, two examples of reactions that have been studied in the laboratory, as well as to some extent theoretically. So this is a ring opening reaction. These experimental results are unpublished yet. We're working with Kaneko on this. So he did very nice experiments where he absorbs these epoxy cyclohexane molecules in carbon nanotubes and observes this reaction. Now, in the bulk phase, this group, Nishizawa et al., 30 years ago, did experiments where they wanted to study this reaction. And so it turns out water is a catalyst. So this is a 5-member ring, epoxy cyclohexane. And if you use this catalyst and you're at 60 degrees Kelvin, and you increase the pressure, eventually the reaction will go. It won't go at low pressure. And so they had to use 1 gigapascal pressure to make this reaction go. So 1 gigapascal is 10,000 bars. And what happens is this 5-member ring breaks one of these bonds and it forms this cyclohexane diol, CHD for short. So now it's a benzene ring with two alcohol groups, two OH groups on the ring. And so this reaction has, and similar reactions have some practical importance because they occur as intermediates in synthesizing pharmaceuticals. So there is some practical interest in this reaction. So when you have this reactant in the pore, it goes, and we don't fully understand that. But the next slide is an attempt to understand this. So this is a density functional theory calculation for this reaction. So it's the cyclopentane going to cyclohexane diol. This is the free energy barrier, the Gibbs free energy, this blue curve. And so this is the 5-member ring molecule on the left-hand side and the product on the right. And you can see this barrier is very high for the bulk reaction. So this is a bulk phase gas reaction. And the thermal energy is about 3 kilojoules, but this is about 191 kilojoules per mole. So it's not going to go at low pressure. So you have to go to very high pressure to get over this barrier. But apparently in the carbon nanotube, it goes without, goes in the presence of water as a catalyst, but it goes without any compression. It goes at 1 bar or even less than 1 bar. And so Kaneko's company have shown this in carbon activated fibers. So these are slit-shaped pores, and they've shown it in carbon nanotubes. Now, the next example, the next slide, is a chemical reaction, but also a phase change. And what's shown here in these gray images are transmission electron micrograph images. And so this is again Kaneko and his team. This was published 9 years ago in Nature Communications. And there are more similar experiments that have been done since by other groups. And so the experiment, they have these carbon nanotubes, and they're in contact with a gas phase at low pressure. And the gas phase in this case is sulfur. And the sulfur absorbs inside these tubes. So this gray line, these 2 gray lines are a line of sulfur atoms absorbed in the nanotube. So this is a pretty large nanotube, 1.1 nanometers. So big enough to absorb these 2 layers. And if you look more closely with other experiments at these layers, you find that they're basically a sulfur polymer chain, which is linear. Now, sulfur won't form a polymer chain like this in the bulk because it's unstable, but it's stabilized by the walls of this nanotube. And so there's very strong wall interactions between the sulfur and the nanotubes, and that's what producing this new phase, nanophase of sulfur. And it turns out this nanophase is metallic. So we've known since we were in high school that sulfur is an insulator. But if you take bulk sulfur and you compress it to about 950,000 bars, almost 1 million bars pressure, there's a phase change to a metallic phase. But that metallic phase is not a linear chain like this. It's made up of zigzag chains packed together into a crystal. So it's a three-dimensional crystal, but it's metallic. So then they tried narrower and narrower tubes. So here, there's a double-walled carbon nanotube. This one was single-walled. So they used both double and single-walled nanotubes. Didn't make much difference to the result. And now you have one single chain of sulfur, and it's a zigzag chain. It's like this. So it looks like the chains in the metallic phase of bulk phase sulfur, but in that bulk phase, there are many such chains forming a crystal. And then if you go down to 6 angstrom units, this smallest chain, you see this linear chain, which is now a straight chain. There's not enough space for it to form the zigzag chain. And so they do other experiments on this thing, and they find the structure, and they find the the sulfur bonding distance. So these sulfur atoms have reacted to form a polymer, and it's covalently bonded together. The bond length is about 2 angstrom units. So the next slide shows the metallic nature of this sulfur, and so this is the resistivity which they can measure, and they do these measurements at different temperatures down to 2 degrees Kelvin. And so the black points are for the empty nanotube, no sulfur. And you can see that this is somewhat conducting. It's a conducting nanotube, and the conduction becomes more and more pronounced as you go to the higher temperatures, as you'd expect. And then when you put the sulfur chain inside these tubes, you get a higher conduction, a lower resistivity. And so there's clearly the confinement has made this this change. So we did some simulations. The work was done by a PhD student named Cody Addington, who I showed his portrait in the beginning. Next slide, I think. Yeah, this is the simulation now. So this is the sulfur chain. We use a reactive potential due to Stillinger and others when they were at Bell Labs. They developed this reactive force field. And you can see these sulfur atoms are very compressed. They're bonded, covalently bonded. So they're no longer simple spheres. And here they are inside the tube. And then we measure various things on this system. And the next slide shows the tangential pressure. And so this is the blue points are the density. So you can see the density is 0 out here. This is the center of the pore. The walls are somewhere out here on this side and this side. And so there's a peak in the density in the center. So all the molecules are confined tightly to the center. They can just barely fit in this tube. This is the 6 angstrom units tube. And the tangential pressure is in the millions of bars range. This is 6 million bars here. And so it's well into the pressure range where you would expect from the bulk, the bulk phase diagram, you would expect this thing to be metallic. So since these experiments of Kaneko, there are other people who've basically copied these experiments, but done it for tellurium and other molecules. They see basically the same results, that a transition from an insulating phase to a conducting phase as you make the diameter smaller. So I'm running over time here. So Fred, please tell me when to stop, because I have an exit strategy and I can stop anytime. But
you can use more time, please.
Yeah, maybe a few more minutes, because I
Yes.
wanted to make some remarks of a chemical engineering nature. So the next slide, I think, this slide is showing, this line is the force between a pair of argon molecules. And so it's plotted against the separation distance, this R. So if we had bulk argon, say in the liquid phase at its boiling point, if you did a simulation, you measure the average nearest neighbor distance, it would be right about this value. This is basically the minimum in the Leonard-Jones potential. So the molecules try to arrange themselves so the repulsive forces balance out the attractive forces, and the force is zero, basically zero. In a gas-liquid interface, the average distance would be larger. This is from a simulation of gas-liquid interface of argon. And this is what produces surface tension. But if we have it in these pores, this is the slit carbon pore that I showed, then the force is way up here in the repulsive region. That's what it is producing, this very big tangential pressure. So the pressure is the force divided by the area. And so now nearest neighbor distance is about 1.05. And this curve is rising very steeply. So this purple region is the repulsive region, and the blue region is the attractive region of the force. But when we go to the sulfur interacting with the carbon, we have this red curve is the force that's felt by the sulfur. And so now these forces are much larger. This is why you see these megabar tangential pressures in the pore. Okay, I want to quickly make some remarks on the next slide. If you think about, and I hope you in the audience, because you have a lot of brain power in terms of thermodynamics, so you may be able to think along the lines of applying that to chemical manufacturing, to think of some novel ways to manufacture chemicals which might be more environmentally friendly, or might achieve some reaction by very high pressures. So in conventional manufacturing, we have temperature, pressure, composition we can control over some range. We can to some extent control some transport variables, and we have all sorts of secondary variables we can do. We can, if we're doing supercritical extraction, we can add promoters or co-solvents. We can put various kinds of electrical and other fields on the fluid that we're on the fluid that's being processed. But one variable that's really important that we can't control over wide ranges is the pressure. Now we go to the next slide. If you look at so-called high pressure processing in industry, the pressure range is up to about 200 or 300 bars. Now, in terms of high pressure experiments in the laboratory, that's not a very high pressure. We often try to do experiments at thousands of 10,000s of bars pressure. We can do that for small samples. And the problem with the industrial systems are that we have very big samples, and the pressure is produced by a compressor. So if you have a cylinder piston type of compressor, you can get a pressure increase of about a factor of 5. And so if you do 3 stages, you've got a factor of 125. But if you go much higher than that, then you have materials problems that basically the compressor will break. And so how do you achieve processing at higher pressures than 300 bars. Well, you could try to develop stronger materials, but that's not going to get you to 10,000 bars anytime soon. And so we're thinking maybe that this compression effect, that's an interfacial effect, might be useful. And so you might say, well, that high pressure only occurs very close to the wall, and it's maybe too small a sample to be useful. But if you just do a quick rough calculation, which is done in the next slide. Okay, so suppose we had a tower like we have for heterogeneous chemical reactions, and we pack it with carbons, which have a very high surface area. And suppose we have a tower of these dimensions, which means that the volume would be about 30 cubic meters. So I'm assuming that the active processing zone might be 2 nanometers. So if you think back to the simulation of the pore of 15 sigma diameter, there were high pressures up to about 2 nanometers away from the mall, and even further away, the pressures were still, hundreds of bars or even 1,000 bars. So this is the density typical activated carbon. And so these carbons typically have surface areas of more than 1,000 square meters per gram. And so if you just multiply these things out, you would have the actual processing zone where the reaction would be going on, or the phase change, would be 30 cubic meters roughly, just rough order of magnitude. So this is similar. In fact, it's a greater processing zone than you would have in a heterogeneous chemical reaction. So, maybe this is feasible. So if I jump ahead to the next slide, you can think of all sorts of, whenever you propose anything novel, there are all sorts of naysayers out there that will say, oh, that couldn't possibly work. And maybe it can't work. Maybe there's things we haven't thought of here. To get it to work, we need better porous materials with less defects, because the defects break up the layers. We need better fundamental understanding. This is probably the most important thing. And you might say, well, extracting the product, but this is done in experiments with solvent extraction usually. Or you might say, well, if I take this product, if the confined nano-phase is my product, I take it out of the pores, won't it just go back and fall apart and be useless? That is true in the case of the sulfur chain. We know if we took the sulfur chain out of the nanotube, it's going to fall apart, because people have tried making sulfur chains in bulk phases. You can't do it. They fall apart immediately. But very often, these confined phases might be the true equilibrium state, and you don't achieve the true equilibrium state in the bulk phase because the barrier is too high. So we saw that with the epoxide reaction. It doesn't go in the bulk phase unless you get to tremendously high pressures, but you can't achieve those pressures in normal industrial processes, so you can't do it. But in the nanopore, it goes to the true equilibrium state, which is the cyclohexane diol. And if you remember, we showed the activation barrier, and the free energy of the product was lower than the free energy of the reactant. So it wants to go to the cyclohexane diol. It just can't get there because of the barrier. But the barrier is greatly lowered when you put it inside this pore. And so in that case, you had a reactant that was in a metastable state, and it doesn't ever go normally to the final equilibrium state because of the barrier, but it will go inside the pore. And we suspect that there may be a lot of chemical reactions where this might be the case. Okay, I'm going to stop here. I'm sorry I'm over time, but if you go to the last slide, there are some conclusions that I basically already mentioned. Future needs include better porous materials. Synthetic chemists are working on this all the time. Every time you open up a journal, you see some new MOF, metal organic framework, or some other type of porous material that and so there are millions of these porous materials now, far more than people have been able to make in the laboratory, but they can be predicted theoretically as feasible materials. Fundamental understanding, we need some agreed upon way to quantify these compression effects. I was showing the pressure tensor, but a lot of people don't like the pressure tensor because at the nanoscale, it's not well defined. We've been looking at ways to get well-defined pressures, but they're coarse-grained pressures. So the forces are well-defined, and so maybe we have to either make do with these coarse-grained definitions, or we have to make do with the forces. So I thank you, and I apologize for the slow beginning, but if we have time, I'll be happy to try and answer any questions.
We're now open to questions. If you want to ask one, please enable your microphone and write it down at the chat and we will read it. Our YouTube viewers can write it down also, of course.
Can I?
Sure.
Kate, thank you very much for accepting this invitation to open our 2022 seminar series. I enjoy a lot your talk, and I have maybe two questions. One is a curiosity. How's the tangential pressure change when you are in the border of the materials? Like you go for a tensor, two-dimensional tensor, two-order tensor, to a bulk phase. And you show a picture in one slide, was I think air in carbon slit pore. That you show some structure close to the border of the pore.
Yes, that's a good question. Yeah, we have studied that, and so the results I was showing are for the nanophase in somewhere in the interior of the pore, well away from the pore mouth. So if you go towards the pore mouth, the opening of the pore, and you track the pressure, then of course the tangential pressure and the normal pressure become more and more similar, and they go eventually to the bulk pressure in the bulk phase, which in most of those slides, the bulk phase was at about 1 bar pressure. And so then as you go through the pore mouth, the tangential and normal pressure become equal. They become equal to the to the bulk pressure, and the bulk pressure is a scalar. It's the same in all directions, and the same on all directions.
But it goes smooth, or
yes, it's smooth. It's in the simulations, it's smooth. Yes.
Okay. Interesting. The other question is, several of these new materials, organic metal framework, they're flexible, a little bit flexible, and maybe cannot reach very high pressure inside, because you may deform the pore structure and decrease the pressure inside. Do you think of what your opinion about this, and if I'm wrong, maybe?
Yes, you're completely right, Fred. I don't think that's been studied. It should be in terms of the pressure. People have studied, they've calculated the effect on the structure of the MOF as you increase the bulk pressure. But as far as I know, I'm not sure if anyone has calculated the pressure in the pore. But what you find in a lot of these MOFs is that if you do an experiment or a simulation, Alain Fuchs has been very active in France in doing these kind of simulations. As you increase the pressure, you often get to some critical pressure where the crystal structure of the MOF changes. And so the whole MOF changes, not just the pore width. And this has been seen in experiments as well. And so it's a different ball game because, as you say, these materials are quite flexible. They're crystalline zeolites, but the pores are very large. And so they're not very, they're not as thermally stable as the small diameter MOFs.
Thank you.
Okay, so now we have a question from Silvana, who has her hand. And after we have a question from Carol Hall in the chat. Please, Silvana.
Oh, okay. Okay, so
hearing me? Oh, now you are hearing me. Okay.
Yes. Okay. Your color.
Okay. I am. I was thinking about how you can use it for supercritical separations. For example, for extracting some material, how the tangential pressure would affect the selectivity, because all the components will also have a high tangential pressure as well.
Yes, that's right. And so the pressure is governed by the forces, typically the forces from the wall. So there are two types of forces on the molecules in the mixture that you're separating. There's the forces from the wall, and there's the forces from neighboring molecules of the different components. And what happens depends critically on the ratio of those two forces. That was the alpha parameter that I showed. And so if you look back, then there's a ratio of well depths of the absorbate, the nanophase molecules with the wall relative to the molecules in the nanophase with each other. So if you had something like a mercury as the nanophase, then the interaction between the mercury atoms is extremely strongly attractive. Whereas the mercury interaction with the wall is relatively much weaker. And alpha is like 0.07 for mercury, whereas for argon or methane, it would be something like 2.5. So they wet the wall much more easily. And so as you change the pressure on the mixture in the bulk, you're also changing the tangential pressure in the pore, and it's a roughly exponential change relative to the bulk pressure. So increasing the bulk pressure by a factor of 2, for example, would increase the tangential pressure by much more than a factor of 2. And so by adjusting the bulk pressure, you adjust the tangential pressure over very wide ranges. And okay. I don't think this has been studied much for mixtures, if at all. But it should be, and it's certainly, it's on our list of priorities. But that would have a major effect on the selectivity, I think.
Okay.
Do you know if people have observed that with, changing the bulk pressure over, say, a factor of 10, how much effect that has on the selectivity? I'm sure it has been.
No, I
Right.
think so, but I do not have the numbers. Thank you very much. Anyway, I have to think how to do this with not only gases, but also other materials.
Okay.
Supercritical pressure can be used a lot for bio-based materials. And that will be very interesting to have selectivity.
Yes, well, as you say, there are a lot of variables when you look at these interfacial systems like absorption into nanopores. You have a lot of new processing variables you could play with, like the pore width, the type of porous material, the the regularity of the surface of the walls, in addition to the usual variables of bulk pressure, temperature, and composition. So there's a lot of work to do, but there are people now applying machine learning to this kind of problem. So they take all the experimental data, they take all the molecular simulation data out there, and they feed it into some machine learning package. They do neural networks or lasso or whatever. I'm not very familiar with these things, but one of my former students that I showed at the beginning, Kai-Hang Shi, is working on this, and he's been sending me his recent papers and so on. It's very impressive work, actually. They can take a vast amount of data, and they know that the results depend on many variables, and that makes it difficult to analyze the effect of pore width, the wetting parameter, and so on, in addition to temperature and pressure and composition. But they are making really good progress.
Okay. Thank you very much. Very good talk.
So there were some other questions. Nicholas Carante sent one. Can you scroll down on that left side? The screen recording is a few options below. Accessibility. That's an old message before we started. Okay. So Carol Hall.
Let me ask my question out loud. Hi, Keith.
Yeah, okay.
So I thought it was very interesting that you said that sulfur will turn metallic if the pressure is high enough. And then I tried to remember how are metals defined? Chemistry is not my strong suit. The question is, do you think other substances would also turn metallic if they were at high pressures?
Yes, I mean, the thing we like about using the pressure as a variable, the in-pore pressure, is that you can find parallels in phase diagrams for bulk materials. And so if you look at, I think it's the group 6 materials, which are sulfur, selenium, tellurium, they've all been studied in these nanotubes. And as you make the tube narrower and narrower, they go from an insulating phase often to a metallic phase, but sometimes there's an intermediate semiconductor phase.
Okay.
And if you look at, just go on the web and look at bulk phase diagrams where people have used anvil cells to measure phase diagrams up to millions of bars pressure, but, very tiny samples, but they can get the bulk phase diagram, and many materials, including elements and compounds, will go from, for example, an insulating phase to various metallic phases at high pressure, or sometimes semiconductor phases.
Okay, cool.
And so I think that it's likely that you can find the semiconductor and metallic phases by, putting these materials in, for example, carbon nanotubes, where you get these very, very strong force fields and very high effective pressures.
Got it. Thanks, Keith.
I don't know if there is another question here from Raja.
Raja, go ahead. Ask.
I think he was just thanking me for the talk. So I'm just reading these for the first time. Jürgen,
You are
Jürgen, I don't know if you're here. You could ask your question, or I can read it.
No, I can talk.
Okay.
Professor Gubbins, you didn't mention anything about the surface tension of the fluids inside the confined tubes. Do they have any relation at all? For example, we studied in our high school, 2 times surface tension by the radius is the pressure. This pressure has any relation at all to this pressures you are talking about?
Yes. Well, in statistical mechanics, you can write equations for the surface tension in terms of these components of the pressure tensor. And so there's a so-called mechanical root to the surface tension that for a planar surface says that the surface tension is basically the integral of Pn minus Pt over the width or over the distance from the wall. And there are corresponding equations for curved surfaces like cylinders and spheres. But there's some controversy about whether that, maybe not controversy, but these equations are not valid when you go to very small dimensions. So you could probably make use of the surface tension for a big pore, maybe a pore of 30 or 40 molecular diameters. But I wouldn't trust them for smaller pores. We've done, there are a whole family of these equations that rely on Gibbs surface thermodynamics. There's Kelvin's equation, Laplace's equation, Young's equation, and so on, which describe the observable effects on the thermodynamic pressure and the contact angle and things like that. But all of these equations break down at the nanoscale. And we've done molecular simulation tests of these equations, and they're only valid for really very large pores. I mean, they'd be valid for macro pores, where you're hundreds of molecular diameters in size. So you're in the center of the pore, you're pretty much have a bulk phase, not a high pressure phase. But you'd have to be very careful about using them at the size ranges I was showing in these slides. I mean, even at 15 sigma pore width, this would not give correct results. And it's off by orders of magnitude, these equations, when you get down to a few molecular diameters.
In your last talk, you mentioned something about the radial distribution functions, if I remember right. Something like 10 separation distances or something like correlation distances.
Yes.
Instead of, a uniform space. How far you can consider a liquid to be uniform after certain distances? So would you say that 5 nanometer you can already consider something like a surface tension idea is valid or not?
Yeah, well, this wetting parameter that I mentioned is a measure of wetting, but it's valid at the nanoscale. If you look at that slide, the definition of this parameter, which I call alpha sub W, W for wetting, then it only involves molecular parameters, things like the diameter of the absorbate molecule, the diameter of the wall atoms, the well depths, the Leonard-Jones well depths of the different interactions. And so you can use that at the nanoscale to describe the behavior. Whereas at the macroscopic scale, people usually use the contact angle. They do an experiment, they put a drop of liquid on the surface, and they measure the angle of contact of that liquid with the substrate. But of course, that's not a valid measure at the nanoscale. And so the advantage of this wetting parameter is it can be used at any scale of length. and so it's sort of like a surface tension, but it's applicable at at the scale we were working at in this talk. So yeah, you can think of these things in terms of Gibbs surface interaction, but Gibbs surface thermodynamics, but that doesn't really apply at the nanoscale because it doesn't take into account these very strong surface forces. So when Young wrote down his equation for the contact angle in terms of the surface tensions, you remember it's just a force balance. That's valid at the macro scale, but at the nanoscale, it's not quantitatively correct because it doesn't account for the very, very strong forces near these interfaces.
But you can invert the question also, right? How can you apply molecular level simulation to nanospace? The nano diameter is almost macroscopic. Again, there will be statistical properties, statistical mechanical restrictions.
Well, that's what statistical mechanics does. It tells you how to extrapolate from the atomic level, the masses and the intermolecular interactions up to the macro scale. So if we had powerful enough computers, we can do these simulations for any size of system. Now they're still somewhat limited, but we can do quite large systems. I mean, people regularly do systems of billions of atoms. Simulations are commonly done. And of course, as time goes on, we can do larger and larger systems. But, for those very large systems, I mean, why would you do a simulation with billions of argon atoms and you show that the hydrodynamic laws are working and so on, but we already knew that, you see. And so the simulations are more useful for studying small systems.
So molecular dynamics is possible for nanomatter system. Dynamics.
Yeah, people have done
without any models.
People have done simulations to verify hydrodynamics at large time scales, and they use billions of atoms. I mean, and you say, well, that's good. We knew that was true before, but it's nice to see it confirmed. But we will be able to do bigger and bigger systems, but the current usefulness is particularly for smaller systems, at least in this sort of field I've been talking about.
Thank you, Professor.
So we now have one last question from Jürgen in the chat, Professor Keith.
Okay. Yes, Jürgen. Okay, can you tell me do you want to tell us the question, or I can read it? I have two questions. One, what type of potential could be used to study carbon-carbon interactions in systems containing argon atoms trapped within graphene, i.e. graphene nanobubbles? And secondly, well, let me answer the first question first. So there are potential models that are partly empirical, partly derived from quantum mechanics that are called reactive force fields. And people have developed those for carbons and silicon and lots of materials. And so they have a part of the potential that's just physical interactions, but they have another part of the equation that's telling how the molecules should bond together. And so there are several of these force fields. They're quite good for carbons. And there's one due to my colleague here at NC State, Don Brenner, called the Brenner potential usually for carbons. We use that quite a lot. And that's a fairly old reactive force field, I think 30 or more years old. But there are more modern ones that are, improvements on Brenner's potential. And So Brenner's potential, if you do simulations, you can produce carbon nanotubes and you can produce different forms of carbon. You can produce structures of hydrocarbons as well with hydrogen atoms. So this is not difficult. Of course, using these force fields, simulations are slower than for unreactive force fields. So Leonard-Jones would be an example of a non-reactive force field. There's no reaction, it's just, you know, physical forces between the atoms. Second question from Jürgen. What would be the mechanism that leads to a decrease in the activation energy of the ECH with water in the activated carbon? It could be a radical mechanism due to the imposed pressure. We don't know the exact answer to that. This is something we're working on at the moment with quantum mechanical density functional theory. But what happens when you confine the molecules, we can say this, I think, is that the activated state becomes different from the activated state in the bulk. So I showed you the free energy barrier for the bulk phase reaction, and it was very high. That's why the ECH stays as ECH, it doesn't react. But I also showed, you probably didn't have time to absorb it, but there was a model of the activated state there. So that's the activated state for the bulk reaction. But in the pore, there is a different activated state, and the reaction path is different. So it's like a catalyst. The pore is acting as a catalyst, and it's promoting the reaction by changing the reaction path. And so if you use density functional theory, you can explore the possible reaction paths inside the pore, and you see an activation barrier, but it's much lower because it's going through a different reaction path and through different intermediates on the way to the final product. So, you know, this is an important research area, of course. And so in some of these cases, you see the high pressures, but there's also other things going on. There's electronic interactions with the wall that produce different reaction paths or different paths to maybe enforce a phase change, like the insulator to metallic. Did that partially answer your question?
Jürgen has typed an okay in the chat for you, Professor.
There's a lot that's not known, of course, in this field.
We have one last question from the YouTube transmissions from Rodrigo Bartolomeu. And he thank you for the talks, Professor. And he wanted to make one comment on the question of Professor Fred regarding pressure calculating and citing IMAFOs. He believes that even taking into account such methodologies as IKEY or the one proposed by Dr. Kai-Han Shi, the definition of pressure itself inside the pores of MOFs is still not clear, mainly because different MOFs can vary largely in terms of symmetry and unit cells. He believes that in a recent talk, Professors Vlugt, Kaledo, and Doubleman mentioned this, i.e. MOFs has holes in all three directions and will be difficult to define a tangential or normal pressure.
Yes, I know. I haven't seen that work that you mentioned, but you're right. I mean, the geometry of the pores in MOFs is a lot more complicated than simple slit pores and simple cylindrical pores and simple spherical pores. So we've studied those three geometries. So a lot of the MOFs would be a bit more like a spherical pore. So as you go from slits to cylinders to spherical pores, you're increasing the confinement for a given pore size, and you're also increasing the force field from the walls. So it's certainly, you know, a good deal more complicated in a MOF, I would say. And so, you know, you would have, you don't have as much symmetry as you had in the cylinders, for example, or the other simple geometries. So yes, it would be more complicated, but it should be feasible to do this. I mean, you can certainly write down the statistical mechanical equations. We haven't done it for the pressure components. Yeah, maybe I'll suggest this to Kai-Heng Shi, because he's the big expert on simulating MOFs now. He's a postdoc in the group of Randall Snur, and they're building, you know, data banks for behavior of these nano-phases in MOFs, and I'm sure he must be thinking about this, but I haven't talked to him about it, and I don't think he's calculated the pressures.
Okay, I think we don't have any other questions, and our time is almost over. So I want to thank you everyone for the discussion, and once again, thank you, Professor Gubbins, for the amazing presentation.